Hey guys, in this video, I'll discuss about arc length and a method on how to find the length of a plane curve. So let us consider the following arc length problem. So suppose we have a function y equals f of x that is smooth on the interval a, b. We define and find the formula for the arc length L of the curve y equals f of x over this interval AB. So, for example, we have this graph of the function y equals f of x, y equals f of x over the, say, interval AB. So this is your A, this is your B. So our goal is how long is this plane curve here? So it will be traced from x equals A until x equals B. Now, we have a terminology that I want to define here. Smooth curve. So what does this mean? So we say that f is smooth on AB if f is differentiable on AB or the open interval AB, and that the derivative of f is continuous on the interval a, b. Okay? So we know that if f is differentiable, then the function itself is continuous. In here, what we want is that the derivative of f itself. Okay? We want the function f prime to be continuous on the interval AB. So if these two conditions are satisfied on the interval AB, then we say that the function f is smooth. Right? So that's a terminology that we'll be using particularly in this type of problem, the arc length problem. So anyway, our goal is to find the length of this curve y equals f of x over the interval AB. And the basis for the computation of this arc length will be coming from a line segment. So in here, we just have 2 points, label x1, y1, and then here we got x2, y2, and we connect these 2 points via a straight line. So the length of this straight line here is given by the distance formula. We find the distance between these 2 points. And if we recall, the distance is just here, square root of x1 minus x2 squared plus y1 minus y2 squared. And if you think of x1 minus x2 as the change in x coordinates, then we just put it as delta x. And of course, if we think of y1 minus y2 as the change in the y coordinates, then we just put it as delta y. So this one here should have been a bigger y. So it's not a subscript. But anyway, so in here we have your y. So anyway, we will use the concept of this distance between 2 points in order to find a formula for the arc length L of the curve y equals f of x. So after finding the formula, it means that, if our curve is not really straight line, we can still find the arc length. Okay, so let us again, draw a curve y equals f of x. Y equals f of x over the interval AB. So let us put an interval here. So this is our A, this is our B. So similar to how we defined definite integrals and also defined or found a formula or derive a formula for area between two curves, we will divide the interval AB into n sub-intervals. In here, um, even if the length of each sub-intervals are not the same, it is okay, right? And the computation won't really matter, okay? So what's important here is in this derivation, we have the following labeling. So let us write that. Divide the interval AB into n sub-intervals. And then we label the points to be x sub 0, which is that's your A, and x sub 0 is less than x sub 1, less than x sub 2, less than until your x sub n minus 1 less than x sub n, and the x sub n is equal to b. So after putting these points here, correspondingly in this ticks on your interval AB, we consider the ith subinterval, ith subinterval, that will be your x sub I minus 1, comma x sub I. And this ith subinterval will correspond to their respective y coordinates. Okay, so in here, we will define y sub I to be f of x sub I. So if we have this subinterval right here, okay, this will correspond, the left end point will correspond to a point that is in here. So if this is our x sub I minus 1, then this one will be the point x sub I minus 1, comma f of x sub I minus 1. And of course, this one here will correspond to this point on the graph. So if this is your x sub I, then this will be x sub I, comma f of x sub I. So in notation, we'll just write that as y sub I. Now, if we try to zoom this, let us take this one here. Let us take this particular part. If we try to zoom this one, the situation would be possibly something like this. So we got this endpoint here, which is your x sub I minus 1, comma f of x sub I minus 1. And then the curve could be looking something like this. So this is your point x sub I, comma f of x sub I. Now what we're gonna do is to find the distance between these 2 points. So the distance is just, the length of the line segment connecting these 2 points. So notice that after zooming it out, it seems that this portion here the red dotted line is almost of the same length as is this part of the curve. Okay? So the length of this line segment will approximate this length of this arc. And of course, if you add more subintervals, let's say we put the other point from here and then added more intervals. So the this will generate a line segment. This will also generate a line segment. And if you notice, if you find the length of this line segment plus this line segment, it will be more accurate to find the length of this curve than using this line segment. Meaning the sum of these two line segments will cover more of the length of this curve than what would this line segment would cover. Okay? So as you increase the subintervals, the number of subintervals, we get closer and closer to the actual length of the curve. Okay? Now, let us continue our derivation. So, on the ith subinterval, ith subinterval, we define L sub I to be square root of x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 squared. That's the length of the line joining the two points. And then what we're gonna do, we can factor out this x sub I minus 1 or x sub I minus x sub I minus 1 squared so that we will be able to write this as x sub I minus x sub I minus 1 squared 1 plus y sub I minus y sub I minus 1 divided by x sub I minus x sub I minus 1 quantity squared, and then we take the square root of this. And then we can actually take the square root of this x sub I minus x sub I minus 1 squared, which is just x sub I minus x sub I minus 1. But that will become our delta x. So after doing the square root of that x sub I minus x sub I minus 1 squared, we will have y sub 1 plus y sub I minus y sub I minus 1 over x sub I minus x sub I minus 1 quantity squared. And outside, we will have x sub I minus x sub I minus 1. And notice that this one is just your delta x sub I. Take note, I said that we divide the interval AB into n subintervals, and it is not necessary to divide it into subintervals of equal length. So we'll just put it as delta x sub I, the length of the ith subinterval. Okay? So far, we have the following. We have Li equals square root of 1 plus y sub I minus y sub I minus 1 divided by x sub I minus x sub I minus 1 quantity squared times delta x of I. Now, from this point, we will need the condition that the function is smooth. Particularly, we need that the function is differentiable on any open intervals inside AB. Okay? So, since f is smooth on AB, f is differentiable. F is differentiable on the ith subinterval x of I minus 1, x of I, for any I. From here, we can apply mean value theorem. And it states that if your function is continuous on the closed interval and differentiable on the open interval, then there will be a C. In our case, we will write that C as our x of I star. So there exists an x of I star inside the interval x of I minus 1, comma x of I, such that the derivative of f evaluated at x of I star, this will be equal to f of x of I minus f of x of I minus 1 divided by x of I minus x of I minus 1. But these are just your y sub i's, correct? So that is just your y sub I minus y sub I minus 1 divided by x of I minus x of I minus 1. So this means that this expression here can be replaced by f prime of x of I star. So L sub I, this will be square root of 1 plus f prime of x sub I star squared delta x sub I. So to find L, what we need to do is to approximate it first using L sub i's. So L is approximated by the sum I from 1 up to n of L sub I, which is sum I from 1 up to n of 1 plus f prime of x sub I star squared. We take the square root of this and then multiply by delta xi here. Then we pass to the limit as n approaches plus infinity. So L equals the limit as n approaches plus infinity of this summation I from 1 up to n of 1 plus f prime of x of I star squared. We take the square root of this and then multiply by delta xi. And if the limit exists, this is precisely the integral from a to b of square root of 1 plus f prime of x squared dx. So this will be the formula for our arc length. Formula for the arc length. So in here, we summarize it this way. If y equals f of x, is a smooth curve on the interval AB, then the arc length L of this curve over AB is defined as this way. And of course, if we think of f prime of x as dy over dx, then we can replace it here. Can also use this one. And then we can also do it if your x is in terms of y. The same situation, right? And just a little correction here. We have here dy, not dxy. So this one would be dy, right? So that's a complete or almost complete detailed derivation of finding the arc length of a curve. Now, during our last meeting, we were able to do this computation. We derived the formula for the circumference of the circle of radius r. Now let us work on our next example. So find the arc length of the curve y equals x raised to 3 halves from 1, 1 to 2, comma square root of 2. So in here, your y is equal to x raised to 3 halves. We get y prime or dy over dx, right? This one is simply your dy over dx. The derivative will be 3 halves x raised to 1 half. Then we square this, the square of y prime. This will be 4 over 9, the square of 3 halves. Oh, sorry, it's 9 over 4, not 4 over 9. 9 over 4, that's the square of 3 halves. And then x raised to 1 half square, it's just x. And in here, of course, if you look at the intervals, the point 1 comma 1 and 2 comma 2 square root of 2. So this will be your A. This is your A. And this is your B. So L will be the integral from 1 up to 2 of the square root of 1 plus 9 over 4 x dx. And then we can calculate this easily. Let's calculate this completely actually. Let u be equal to 1 plus 9 fourths x. Du will be 9 fourths dx, or that 4 over 9 du, this is equal to dx. So this one becomes integral square root of u times 4 over 9 over 9 du. So this will become 4 over 9 u raised to 3 halves divided by 3 halves. Evaluated from somewhere to somewhere. But let us bring back the variable x. The coefficient becomes 8 over 27. And then we will have here 1 plus 9 over 4x. Then we evaluate this from 1 up to 2. So calculating, we will have 8 over 27 times 1 plus 9 fourths times 2, that will be 9 halves, minus 1. Oh, I missed something. I forgot the 3 halves here. So let me just insert that 3 halves. So this one is raised to 3 halves, evaluated from 1 up to 2. So this one here will be raised to 3 halves, then minus 1 plus 9 over 4 raised to 3 halves. So you can simplify this, but I'm completely fine if this is your final answer. Right? Next problem. Find the exact length of the curve x equals 1/3 of 1 y squared plus 2 raised to 3 halves from y equals 0 to y equals 1. So find the exact length of the curve x equals 1/3 of y squared plus 2 raised to 3 halves from y equals 0 to y equals 1. So first, we have here x equals 1/3 y squared plus 2 raised to 3 halves. X prime, this is simply your dx over dy. So this will be 1/2. So 1/3 times 3 halves, that's 1/2. Y squared plus 2 raised to 1/2 times by chain rule multiplied to 2y. And this becomes y times y squared plus 2 raised to 1/2. And then square it, x prime squared. This will be y squared times y squared plus 2 raised to 1/2 squared. So it disappears. Therefore, we have L equals the integral from 0 to 1 of the square root of 1 plus y squared times y squared plus 2 dy. Now, we can rewrite this as the integral from 0 to 1 of the square root of 1 plus y to the 4th plus 2y squared dy. And if you can recognize this is actually a perfect square trinomial, which can be written as y squared plus 1 quantity squared. Then you take the square root of this dy. So this simplifies into integral from 0 to 1 of y squared plus 1 dy, which is now y cubed over 3 plus y, evaluate from 0 to 1. So this will be 1/3 plus 1, which is equal to 4/3. Okay. Now let's consider the next example. Find the arc length of the curve y equals x to the 6 plus 8 all over 16x squared from x equals 2 to x equals 3. So let's rewrite y as x to the 6 plus 8 all over 16x squared. We can rewrite this as 1 over 16 x to the power 4 plus 1 over 2, that's 8 over 16. And then we have here x to the power negative 2. Then we can take y prime. Y prime will be 1 over 4 x to the power 3. Then here, this becomes minus x to the power negative 3. Okay, so negative 2 will go down. So negative 2 over 2, that's minus 1. And then minus 2 minus 1, that's minus 3. So this is our y prime. We square it. Y prime squared. We will have 1 over 16 x to the power 6 minus twice the product. Twice the product, that becomes 1 over 2 times x cubed times x raised to negative 3. So they will cancel each other. Then plus the square of x raised to negative 3. This is x raised to negative 6. So our L, let's write our L here. L equals integral from 2 to 3 square root of 1 plus 1 over 16 x to the 6 minus 1 over 2 plus x raised to minus 6 dx. And then here you have 1 minus 1 half. 1 minus 1 half. So you will have here integral from 2 to 3 square root of 1 over 16 x to the power 6 plus 1 half plus x to the negative 6 dx. Now if you look at this, 1/4 x cubed minus x raised to negative 3, if you square this, we obtain this one here. The minus here came from this minus. Now, look at this expression. This is almost the same as this, except that we now have a plus. Okay? So if you have observed that and analyzed that nicely, this expression inside the square root is just 1 over 4 x to the power 6 plus x, not to the power 6, but to the power 3, plus x raised to the power negative 3 squared dx. Okay, so this expression here is equal to this expression here with that squared thing. If you don't believe, then try to expand this and you will end up with this expression. And therefore, this just becomes integral from 2 to 3 of 1/4 x cubed plus x raised to power negative 3 dx. We got the square root of the squared. So square root of this squared. Therefore, we'll just have 1/4 x to the power 4 divided by 4 plus x raised to negative 2 over negative 2. We evaluate this from 2 to 3, which means at x equals 3, what do we get? 3 to the power 4, that's 81. 3 times 3, that's 9, but that's 3 squared. So 3 to the power 4 is 9 squared, which is equal to 81 over 16 plus x raised to negative 2. That's, you can put this one on the denominator, and this is a minus, so let's just put the minus. We have minus 1 over 2. So we are putting this on the denominator. That becomes 3 squared, which is equal to 9. Then minus, we got here 1 over 4, 1 over 16 again, but 2 to the power 4. 2 times 2, that's 4. 4 times 4, that's 16. So this will cancel. So we'll just have 1 minus 1 over 2 squared, 2 times 4. And you can simplify this, but I'm all good with this as a final answer. Okay, now you can work on this example. You want to find the arc length of the curve 24xy equals y to the 4 plus 48. So choose which or how you will write your function. But anyway, I think you can just write this as x in terms of y, simply because this is y to the 4. Here you just have x. That's the highest power of your x is 1. So if you divide everything by 24y, then you will be able to write this as x in terms of y. And furthermore, you get y equals 2 until y equals 4. So write x in terms of y. So I will leave that to you. And as a reading assignment, um, try to, well, study this part here. Arc length of curves defined by parametric equations. We are not considering, it is rare in this course, Calculus 2, that we will be doing parametric equations. Okay? You might find this topic, parametric equations, in your Calculus 3 if you're going to do Calculus 3. But there is a corresponding formula for arc length if your curves are defined via parametric equations. So as a reading assignment, which is also in your handouts, please try to study this and try to work on some of these examples. Okay, so that's all for this topic, and thank you.